As developers, we're always focused on building apps that just work smoothly, flawlessly, no matter what. But to really pull that off, we have to understand the invisible world our data is flying through. So today, we're going to pull back the curtain and look at the actual physics that control every wireless network, from your Bluetooth headphones all the way up to global 5G, so we can build better, tougher, more resilient applications.
All right, let's kick things off with this because it's a huge idea. In the long run, every application is a wireless application. I mean, think about it from a user's perspective. They don't know and they don't care if they're on fiber at home or a spotty cellular connection on a bus. They just expect your app to work. For them, there's no difference. So for us, as developers, that means we absolutely cannot ignore the realities of wireless. But here's the silver lining. Every single optimization we make for a bad wireless connection ends up making our app better for everyone.
So here's the game plan for today. First, we'll talk about why user expectations are just so incredibly high these days. Then we'll get a lay of the land, mapping out the different kinds of wireless networks. After that, we dive into the single biggest challenge they all face, something I like to call the cocktail party problem. We'll look at the one formula that's basically the speed limit for all of them, figure out why you never get the speed you see on the box, and wrap it all up with a practical survival guide just for us developers. Let's start right here, with the world we're all living in. That expectation of being connected all the time, reliably, it's not a feature anymore. It's the absolute baseline. You know, our users are constantly on the move, and they're hopping between networks without even thinking about it. They're on Wi-Fi at the coffee shop, then they jump to LTE on the walk to the subway, and maybe they're using Bluetooth to connect to their watch the entire time. We can't just build for that one perfect scenario on our office network. We have to expect this chaos and design our apps to handle it gracefully. It's not optional. It is absolutely essential. So we've got all these different wireless technologies floating around. How do we even begin to make sense of it all? Well, a really good way to start is just to group them by how far they're designed to reach. We can pretty much break the entire wireless world into 4 main zones. First up, you've got your personal area networks, or PANs. This is for stuff right in your personal bubble. Think Bluetooth earbuds or tapping your phone to pay with NFC. A little bigger, we have local area networks, or LANs, which cover a building or maybe a college campus. This is your classic Wi-Fi. Zooming out even more, you get metropolitan area networks, MANs, which are built to cover an entire city. And finally, the big one, wide area networks, or WANs, which give us that worldwide access, like the cellular networks our phones are always connected to. Now, here's where it gets really interesting. These neat little categories, they're constantly blurring. Technologies don't stay in their lane. Bluetooth started out as a way to replace the simple cable, right? But now it can smartly hand off to Wi-Fi if it needs to transfer a big file quickly. And a modern app might use all of these in the span of a few minutes. You might use NFC to pay for a coffee, then Bluetooth to share a photo with a friend, and then Wi-Fi to stream some music. The key takeaway here is that our apps have to be smart enough to navigate this complex, multi-networked world without missing a beat. All right, let's get to the heart of it. There's one core challenge that every single one of these technologies has to deal with, and it's something you already get intuitively. We're going to call it the cocktail party problem. So, just picture it. You're at a loud, crowded party. Music's blasting, everyone's talking. To have a conversation with the person standing right next to you, you have to practically shout. You probably go home with a sore throat. Well, if you can picture that, you've already grasped the most fundamental concept in all of wireless physics. And this visual just nails it. Look at the left. In a quiet room, 2 people can talk easily, even from 20 feet away. Their voices are the signal and there's almost zero noise. Easy. But now look at the right. At a packed party, every other conversation is just background noise. To be heard, you have to get closer, you have to talk louder. The distance you can effectively communicate over shrinks a lot. This relationship between the signal you want to hear and all the other noise around it is the single most important thing that determines wireless performance, period. And this leads us to our first big technical term, the near-far problem. Back at that party, if someone is shouting right in your ear, you have absolutely no chance of hearing what your friend is trying to say from across the room, right? The loud, nearby voice, the strong signal, completely drowns out the weaker, distant one. It's exactly the same for a wireless radio. A powerful transmitter nearby can completely blind a receiver to a weaker signal that's farther away. And the second effect of this is really cool. It's called cell breathing. So as more people show up to the party and start talking, the total noise level goes up. And everybody's little conversation bubble has to get smaller. In a wireless network, as more devices connect and start transmitting, the interference level rises, and the effective range of that cell tower or Wi-Fi router actually shrinks. It breathes in. And when people leave and it gets quiet again, the range expands. It breathes out. So we've got this great intuitive grasp on signal versus noise. Now let's put some math to it. Let's look at the beautiful, elegant law that describes this relationship and sets a hard speed limit for every wireless channel in existence.
This is it. This is the whole shebang. It's Shannon's channel capacity formula, and it is basically the universal law of physics for wireless communication. It tells you the absolute theoretical maximum data rate, or capacity, that you can possibly squeeze through any given channel. And what's amazing is that it all boils down to just two main things.
Okay, let's break this down because it's not as scary as it looks. C is for capacity. That's your top speed. It's the number on the box. BW is bandwidth. You can think of this as how much of the airwaves you get to use. The classic analogy is a highway. The more lanes you have, the more traffic can get through. And finally, you have SN, which is the signal-to-noise ratio. And hey, that should ring a bell. That is the cocktail party problem, turned into math. It's simply a measure of how loud your signal is compared to all the background noise. Now that first variable, bandwidth, is super interesting. The radio spectrum isn't some infinite resource we can all just use. It's a finite thing, just like land. And just like land, it's zoned, it's divided up, and it's heavily regulated by governments. What you're looking at here is a chart from the FCC that shows just one tiny sliver of that spectrum and how it's carved up for everything from TV stations to your cell phone. And because it's so scarce, it is insanely valuable. In a 2008 auction here in the US, a slice of the 700 megahertz spectrum sold for almost $20 billion. That's billion with a B. So the point is, bandwidth, one of those two key ingredients for speed, is not free. It's a finite, incredibly expensive, and heavily contested commodity. Okay, so we've got the theory, we've got the formula. So why is it that the up to 600 megabits per second that's advertised on your router box never, ever seems to happen in real life? Let's connect that perfect theoretical world with our messy actual reality. Well, that big number on the box is calculated assuming absolutely perfect lab conditions. It's like being the only person in the room at that cocktail party, standing right next to the person you're talking to. It assumes zero background noise, zero interference, and that you own the entire channel. But your actual real-world experience is a constant fight against physics. Your speed depends on how far you are from the router, background noise from stuff like your microwave oven, interference from your neighbor's 20 other Wi-Fi devices, even the battery level on your own phone can make a difference. And here's the really clever part. Your devices are constantly adapting to these changing conditions. There's a process called modulation, which is just how they turn digital ones and zeros into analog radio waves. When the signal is super clear, when you have a high signal-to-noise ratio, your phone uses a really complex language to pack a ton of data into each signal. The result? Super fast speeds. But as a signal gets noisy and weak, it automatically switches to a much simpler, more robust language. It's slower, yeah, but it makes sure the message actually gets through. This constant, automatic shifting is precisely why your Wi-Fi speed seems to go up and down from one moment to the next. Okay, we've done the physics lesson. Now it's time for the payoff. What can we, as developers, actually do about all this? How do we build apps that don't just survive, but actually thrive in this chaotic wireless world? All right, these are the essential strategies that should be in every developer's playbook. First and foremost, cache aggressively. You have to remember, the fastest and most reliable network request is the one you never have to make. Second, compress everything. I mean everything. Every single byte you can shave off your data payload is a huge win on a slow network. If you're streaming audio or video, adaptive bitrate is non-negotiable. It lets the quality shift up and down based on the user's real-time connection. And when connections fail, and trust me, they will, use an exponential backoff for retries, so your app doesn't just spam an already struggling network. And finally, always look for ways to bundle lots of tiny little requests into one single bigger request. It cuts down on a ton of overhead. And this might be the most important piece of advice in this entire explainer. You have to test for reality. Your lightning-fast, super stable office Wi-Fi is a lie. It's a fantasy land. It does not represent your user's experience in a crowded airport or on a 4G connection with 1 bar of service. So use the network throttling tools that are built right into your browser's dev tools. Use dedicated tools like network link conditioners. And please, actually get out of the office and test on real phones on real cellular networks. So,
I'll just leave you with this final thought. By understanding the physics of the cocktail party, the universal speed limit, and the messy reality of the wireless world, we can finally stop building apps for the quiet, perfect conditions of our office and start building them for the chaotic, unpredictable, and exciting world where our users actually live.